Okay. All right.
There's a lot.
I did want to quickly. I realized 34 is probably complicated enough to warrant going back to like. Let's make sure there's no confusion on it. Even though we've kind of talked about it before, but this does touch on some older stuff.
I had to look up the.
So this is 34. Okay, so this block is being pulled at a 37-degree angle with a 100 Newton force, and it's a 10-kilogram block. And it says we know the mu value, 0.4, and we know that the block is pulled a distance of 5 meters. Oakley dokley? Okay. First question, how much work was done in the block by the person pulling it? So the work done on the block, so let's maybe call this the work done by the pull, is going to be the, this vector here, right? It's the vector that's actually along the direction of motion. So that would be, how big is that vector?
100 times 37.
100 times the cosine of 37. So that's the force. So remember, this is the central idea here. Work equals force times distance, right?
Yeah.
So the force is this, and the distance is 5. Okay? Let's ask Mr. Quackolator how big that is.
79.9.
Okay. Thank you. Now,
Wait, which one did you just go for?
this one?
Not that, yeah, that was the, never mind, that's wrong.
That sounds really small, actually.
Yeah, 79.9 is the 100 times cosine of.
That's what we're asking.
So it's going to be like 400-ish.
299.3.
Okay. Okay, everyone okay with that?
Yeah.
Oh wait, I have the wrong unit. I was just testing you. Not really, I just made a typo, but do you see the typo?
Joules.
Joules, not newtons. You can't say the work is newtons. That's crazy.
We will have
Joules. Okay? So there's how many, that's how many joules of work were done on the block. Now, first thing, what value was completely irrelevant to this calculation? True, mass. Good point. What else? I didn't think of that actually. That's a good point. Mu. So if you just want to know how much work did you do on the block, well, we didn't even have to think about mu yet. Now, mu, of course, is going to come into play here. How much energy would be lost to friction? Well, same principle. Work equals force times distance. If I want to know how much energy was lost into friction, I want to figure out how much work was done by friction. Okay? So the work done by friction would be, now here's where it gets a little interesting, because you have to do, what's the force of friction? Mu times the normal force, and the distance is going to be 5. But we got to go back to the diagram and do a little bit of force diagramming, right? So
Yes.
Look at your force diagram. How much force pushes down? 98. That's called gravity. Okay. Now, how many forces are pushing up on the block? 2. There's the floor pushing up, and there's also this vector pulling up. So, since this is 100, you have to figure out, well, what? We'll see if I've completely failed you as your physics teacher here. Do we know how big that vector is?
Sorry, 100 something.
Yes, thank you. You're the best. Okay, so this is the component, right? This vector pulls up with 100 times the sine of 37 newtons. And there's also the force that we call the normal force. So quick little calculation here. This is a good space for the calculation, by the way, up here next to the diagram. The normal force plus this 100 sine of 37 should have to balance out to 98. So the normal force is just going to be, by the way, looking ahead, when you do 35, think of where these numbers came from. F sine of theta, this is mg. Although on 35, it's being pushed downward, so you're actually going to end up with an addition of two vectors. But anyway, what does this end up being? What number is this? 98 minus. Oh, great, Mr. Quackolator. What is 98 minus this? What do we got?
37.82.
Everyone agree? Okay. Sure everyone's in agreement here?
Yep.
Okay. So my friction force is going to be mu, which is 0.4, times the normal force, which is 37.8. Okay. And then times 5.
So we talked about this.
Okay. Does everyone feel okay about that? And then the last question is, what's the block's final velocity? So you might notice there's a decent amount of space there because not that it's going to be a huge process of calculation, but what's the net change in energy of the system?
A minus B.
Exactly, A minus B, this minus this, right? So he started off with no joules. There was this much work done into the system. This much work was taken out of the system. So if I write something like his total energy, or as I should say, his change in energy, is work in minus the work out. So if I subtract those numbers, I get his final energy, which, what does that come out to be? 320.
3.8.
Is that right? You subtract them? A little bit early for arithmetic.
Yeah, that's right.
Seems right. So what I would do then, what am I going to set that equal to if I want to know his final velocity? In what form is his energy stored right now? Kinetic. So I can just set 323.8 equal to 1/2 m v squared and solve for v. Divide by 5. Square root. Should get like something in the realm of 8. Something
8.05.
Okie dokie. So if you look at 35, yes.
What numbers did you use for work in and work out?
Okay, so work in was the work done by the pull.
Okay.
When I say in, let me clarify that. So in means going into the block, basically. So when you push the block or pull the block, you're kind of putting work into that system. And the friction, he's kind of doing work that takes it out of the system. So work out would be this. So if you look at 35, it's the exact same. Just I would definitely use 34 as a guide here. The big difference between 34 and 35, other than having no numbers, is this diagram is going to be slightly different. So this vector points this way. So you're actually going to have F sine of theta in the same direction as the mg. So your equation is going to be F normal is equal to mg plus F sine theta. Versus here it was subtraction, which you'd end up with. That's really the main difference. Oakley Cadokley? Yes, maybe, possibly. Let's do one or two power problems, and then I want to hopefully let you have at least 15 minutes to just knock out a few. Power. What?
Nothing.
Maybe one of the graphing ones.
Which one?
Not one of the graphing ones, one of the ones with the chart on it.
Yeah. I mean, you're just gonna like for Alfred, Bert, and Carl.
Birds.
Bird.
Yeah,
Bird nerdy.
What about Alfred?
What about-
That's a new character too. Alfred.
We got Calvin and Dave on there.
Yeah.
Ooh.
No, that's Albert and Bob. They're back. They're reprising their role.
Yeah. Oh.
I like Calvin.
What can I say? I'm a creative genius. You know. J.K. Rowling came up with all those creative names in those books. This is just as creative in my opinion.
Mhm.
Oh, look, you got your Hogwarts shirt on. That's an homage to Alfred, Bert, and Carl, obviously. Which Hogwarts house are you, Kate? Ravenclaw? That's, I like to be in the house of the good guys personally. The snake. Hiss hiss. I still can't believe they bullied him so much in those movies. And it was like, yeah.
Not that movie.
He's just going to school, trying to like follow in his father's footsteps, be the best he can be, and then these kids bully him mercilessly the entire film. No, the entire series of films. There's like 8 of them.
The entire 8 years.
8 films. Yeah, it's a tragic story. I just don't really. It's crazy. Can you believe that, Julia?
No.
That one old guy just arbitrarily awards the victory to the bad guys for literally no reason. My goodness.
It was for playing a
Well, they're
game
living
of
in
chess.
society.
Yeah.
What?
It was for
Yeah.
playing a game of chess.
What was chess?
That's why the bad guys won.
For chess?
Yeah.
We don't remember the Super Bowl.
In the first movie.
No, the big chess game.
There's one for you, Zach. I'm pretty sure that Ron plays the Scandinavian in that chess game. Pretty sure.
You do.
He does? Is that correct?
That's what I heard.
Or no,
That's-
the computer plays the Scandinavian because Ron's white, isn't he?
So he just plays.
I think Ron plays E4, computer plays D5.
And then takes.
Wait, hold on. No. Ron is black.
Oh, so.
Because the
he plays
computer,
same thing.
the ghost or whatever plays E4. Ron doesn't really know exactly how this works, so he plays D5, and then
Yeah.
well, they take his pawn. Is that right?
Is it, and then it's queen takes on D5.
This is my favorite conversation.
Was that from the first movie?
Yeah.
That's how Dumbledore gives him the win.
Yeah.
Are you telling me that Ron Weasley doesn't know how to do a perfect Black Martini Gambit? Or that so should have a dangerous counterattack?
No, I guess not. Anyway, sorry. These movies are very triggering to me. Okay, so this just says rank the power output. So Alfred, Bert, and Carl. The reason this question is not obvious who is the most powerful cyclist because they have different masses, different initial speeds, different final speeds, and different periods of acceleration. So, like for example, Alfred is the lightest of the cyclists. He gains 6 meters per second of speed over a very short period of time. Carl is the heaviest. So by the way, if you're heavier, would you tend to be if all other things being equal, say two people accelerate up to, same acceleration, same time period, but one person was heavier, who's more powerful? The heavier person, like, to use a football reference, like for a defensive, like a big 300-pound defensive tackle to accelerate, up to top speed, it takes a lot more power than for like a small like wide receiver, right? Okay, assuming they're accelerating to the same final speed over the same time frame. But
Wide
anyway,
receiver, you run as defensive tackle, you replaced.
true. Some of those guys, although on short bursts, those big players are surprisingly fast.
Yeah.
Okay, so
Like Officer Barnes.
These guys are like,
Well,
50
they
times
have
heavier.
before than they have.
Yeah.
I'll show you the calculation for one of them. You guys can complete the rest.
Wait.
This is Alfred.
Oh, I'm very sorry. I'm very sorry. Totally different person. Alfred, not Albert. Sorry, Alfred. An homage to Alfred Eisenstein, the man who invented gravity. Right, Julia? Okay. Alfred, his power, right? So his power is the change in energy divided by time. Okay, so what's his change in energy? Well, you could do it all in one big expression if you wanted, or you can just go down on the side and go, well, what was his initial energy? He initially had 1/2 m v squared, right? Does that make sense? So 30 times 25, 7. Is that right? Please help me with the calculator. Don't let me embarrass myself up here.
Take off the
I think
zero.
is it just 7? Sorry. Lamau, just testing you, obviously. Let's see. What was his final energy? 1/2 m, same m, times 11 squared. What is this?
What is it called?
Is that right?
Yep.
Did I get it?
Yeah.
Yay! I did it. Tough one. So, what was his change in energy? You gotta subtract him, right? You have to make this stupid arithmetic. 20.
No, you're making us do this stupid.
You have a calculator. Is that right?
2880.
2880. Guys, make me sit up here and suffer. I didn't even have my Bang Sody Pop today yet.
Is it 2080?
Is it?
Yeah.
Yes, it is.
Yeah. Okay, if you give a calculator, you're still getting it wrong. I don't know what to tell you. You got to be able to do it with calculator. Okay, time. How much time did it take him? Well, it took him 3 seconds. So go ahead and divide those. So that many joules over that many seconds.
960.
Okay, 960 watts. Okay, almost a kilowatt. That's pretty good. By the way, Alfred is considerably over 1 horsepower. Good job, Mr. Horsey. You did it.
A horsepower and a quarter.
Yeah.
Just about.
So all you're gonna do in this problem, the main reason that I put this problem on here, if you're wondering, is I wanted you to really understand that you have to calculate these two energies separately. A lot of people are tempted to go, oh, well, 11 minus 5 is 6, and then have like a 6 squared in their calculation. That would be very, be it. Okay, don't do that. So all you're gonna do in this one is calculate separately the 3 changes in energy and the power, and then compare them, and then you rank them. Okay? All right, so I'm gonna move on. Just leave yourself a note that maybe that you still got 2/3 of the problem to finish. I want to just do one of these where it's like let's look at 42, maybe 43. I want to make sure I do one where it's talking about a constant process. So we'll do, I guess we can do 42. 42 is not too exciting. Take a second and read that one. We're gonna do 42, and then we're gonna go. We'll do 46 and 47. Okay, so 42 says Bob is gonna run up a ramp. Okay, here's your ramp, Bob. Here's Bob. Bob is 80 kilograms. And the ramp is a 10-meter tall ramp. He's going to run up the ramp. And he does this in a way so that at the top, he's traveling 7 meters per second. So he is sprinting up this ramp. So he's, what kind of energies is he gaining? Potential and got it. So all you got to do, the question asks us to find his power output. So by the way, the time this took was 16 seconds. Okay, 16 seconds. So his power is his change in energy divided by how much time it took. So let's look at how much energy did he have down here? Assuming he had no energy. And so his total energy up here would be his mgh plus his 1/2 mv squared. And then it gets divided by its time. So the calculation would go, his mass is 80. 80 is 9.8 times the height, which is 10. Plus 1/2. His mass is 80. Velocity at the top was 40 or 7 squared or 7. Sorry, velocity. It's divided by 16. So we ask Mr. Quackulator, that many joules divided by that many seconds.
622.5.
That's it?
612.5.
Oh, my bad.
I did say.
Let's try to squeeze a 1 in there. Calculate. Is that what everyone got? All we got? Okay. Fortunately, we're going to end up with like 10 minutes of work time. Sorry. Tomorrow's going to be a work day.
That's not acceptable.
We do not accept your offer.
Of what?
Instead, we raise you to watch movies.
To watch what? We can just watch videos of my new hero in life, my new idol, Victoria from The Bachelor. A true paragon of virtue.
Hey, she got voted off last night.
No, she did not. What?
You spoiled it.
Emily. Are you lying?
No.
You're lying, right?
No.
I need to go home.
Did you
I'm gonna take a day off for grief. It's a sick day too, not a personal day, Kate.
I was watching a video and it was I was not
Let's have a moment of silence for Victoria.
Because everybody on that show is okay and not crazy.
No, I know that. I believe that. You get to make big place people.
It's dumb.
All right.
And the time.
So I wanted to make sure that we go over 47 because you might look at 47 and go, this is an example of a problem where you, if you use that technique of listing out the given information, if you go, oh, this problem's about power. Okay, well, I know my formula for power, so I write my formula. And then you go, oh, okay, well, they're giving me a mass, and they're giving me a speed. Okay. you might run into some confusion because you might go, well, wait a second. If this thing's being pulled upward at a constant speed, notice the question does not say how much power is required to accelerate it from 0 to 4 meters per second. You understand the difference? Because that requires power to accelerate something, but this is just talking about two moments. Let's say that, call this moment 1 and this moment 2. It's being lifted up by a winch, right? So how much kinetic energy does it have here versus here if it's going at a constant speed of 4 meters per second? It's the same. Everyone understand that? So what you could say is the change in kinetic energy is nothing. There is a change in potential energy though. Okay, that's going on. Okay, so what you do is you say, well, okay, let's examine a time period. Who can think of a nice time period we could look at, an interval of time that would
1 and 2.
like time 1 and time 2?
Yeah.
Yeah, I was just gonna say like a 1 second time period. Yeah, you got the.
Yeah. 1 second, 2 seconds.
Yeah, so let's look at a 1 second time period, or you could do a 2 second time period if you wanted to. But let's look at a over a 1 second period. Let's watch what happens. Okay, the block is here, and then the block is here. How far would it have traveled upward in 1 second? 4 meters. Okay. And so if I want to talk about the change in potential energy then, I can go M, what's the M, 100? M, G, H, because that's the height it was raised, right? Divided by, how long did it take? 1 second. So turns out look how, so it's a surprisingly easy calculation, right? But what's very confusing for a lot of people is they go, wait a second. You basically put this V value in for H. Kind of weird, right? But that's the way it works out. If you had examined a 2 second period, same calculation. If it had been a 2 second period, this would be a 2, but what else would have changed? This would be 8. So proportionally, it's the same. So, okay. That's all I got for you for today. Thanks for the 100 gifted subs.